Good morning.
Good morning. All righty. It's 8 o'clock. We're going to go ahead and get started. We're going to finish up what we 5.3, and I added some. I'm going to try to record this. I added some slides to the last lesson. And so we'll go over that real quick. So this is 5.3. We went through inverse functions, and we talked about the function and set of ordered pairs, and to find the inverse of set of ordered pairs, you switch the x and y terms, and also the domain and range switch as well. So that's nothing new. And we talked about the steps to find the inverse functions. Substitute in y for f of x, switch x and y, solve for y, replace y with f of inverse symbol, and then check by applying the composite functions, and you should just get x. We looked at graphs, where if you switch the x and y components to a particular point, you can get the inverse graph. And we looked at finding the inverse, looking at the function and its inverse, substituting one in as a composite function, and we should just get x out. And then we looked at the horizontal line test. In order for a function to have an inverse, it has to be 1-to-1. And if it's not, you can place restrictions on it to make it 1-to-1. And we talked about monotonic, where the function is either increasing through the entire domain or decreasing through the entire domain. So function would have to be monotonic in order for you to get an inverse function from it. If not, then you can't get the inverse. Using the horizontal line test, we looked at these functions as well. And I added a new slide to the presentation yesterday. So you want to write this down. If you have a B number, we'll call it B, going into the function, your answer will be A coming out. The inverse, you can switch that. In the inverse, you have A, the output of F, or the Y value of F. If you put the Y value into the inverse function, you get the X value out. So you can literally, once you find the X and Y, the independent and independent variables, you can literally switch them to get the dependent and independent variables. So to find the derivative of an inverse function, basically, if you find the derivative of the original function and then apply the reciprocal to it, and you can find the derivative. So this is a much simpler way to work through the problem that we worked through yesterday, and we're going to use that today. Okay, so why is this not moving? All right, so let's take a look. Oh, all right, for some reason, I'm having some problems here. Let's try this again. Why is this not working? Okay, let me try something here. I'm having some problems with my screen share. Okay. So turn this back on. There we go. That's better. All right. Okay, here we go. All right. So first thing we do is we change f of x into y. So we were on this slide here. Now, the next slide, change f of x to y, substitute the a value for y, and solve for x to get your x value, and that's going to be our b. And then there's, in some equations, you can just solve for x, but others, where you can't solve for x, then you can either use synthetic division or you can just use the calculator. We're going to use the calculator. Set the equation equal to 0, graph it, use second, calc, and then 2 to find the 0. And once you find the 0, then you find the x value. Okay, so we're going to look at that. Therefore, since f of b equals a, so once we find x, we find b. So we're given the y value, and we got to find b. Once we find b, then the inverse function, you just switch these two, and the output to our function is the input to our inverse function, and we get the b value out. So you can switch these just like we did with the ordered pairs, from the function to its inverse and so on, the graph and so on. Find the derivative for f, our original function, and then substitute the b value in for that. And so to find f of a equals to, all you do is you take this answer and you just apply the reciprocal. You just flip it. In other words, the answer is reciprocal to step 5. All right, so let's take a look at another problem here. We're going to look at problem number 63. All right, so let's get a marker. Okay, so problem 63 is we have f of x equals to 5 minus 2x cubed, where a equals to 7. Okay, so this is actually y equals 7, or f of x equals 7. Okay, so this is basically, we're given the y and we have to find x here. So we replace, so step 1, change f of x to y, substitute a in for the y value. Okay, so this becomes y equals to 5 minus 2x cubed, and then we put a in for y. So a is 7, so we put 7 in there. equals to 5 minus 2x cubed. Any questions with that so far? Okay, now for here, we could solve, there's only one x value, x cubed, so we don't need to apply the calculator. So we can just apply minus 5 to both sides, and we get 2 equals to negative 2x cubed. And then from here, we can just divide by negative 2, and we get negative 1 equals to x cubed. And then we just apply the cube root. Since x is cubed, we have to apply the cube root so that the cube root and the cube cancel each other out. And we get x equals to a negative 1. Now, when you have an odd root, you don't have to worry about imaginary numbers, because negative 1 times negative 1 times negative 1 is negative 1. It's not like when you have even roots. So it's okay to get a negative for an odd root. Okay, so from that, now we have our x value, right? Now we have negative 1, 7. Okay, so now the next thing we're going to do, so we found our x. Okay, so we don't need to apply the calculator because we were able to solve it directly. Therefore, since f of b equals a, then f inverse a equals b. So, so that means the inverse to this function is going to be 7, negative 1. So the function we put in negative 1, we get 7 out. So if you put negative 1 in here, negative 1 cubed is negative 1. 2 times negative 1 is negative 2 times negative 1 is positive 2. 2 plus 5 is 7. So it checks. So you have our function, you have x is negative 1, 7 going out, and the inverse is 7 going 1, and you get negative 1 out. Okay, so now we're going to find the derivative of our function. So we take this f of x, I'm just rewriting this original function, 5 minus 2x cubed, and now we're going to find the derivative to that. Well, the 5, that goes to 0, right? And then this will be 2. We bring the 3 down and subtract 1, right? And so this will be 2 times 3x to squared. So our derivative, f prime x, is equal to negative 6x squared. Okay, so that's our derivative, and that's what we did here for step 4. Okay, so now we substitute the b value, or x, into our derivative. So this will be f prime, and so we found that to be negative 1, right? So I'll just underline it. So we put negative 1 in here equals to negative 6 times negative 1 squared. Well, negative 1 times negative 1, right, is 1. So 6 times 1 is a negative 6 times 1, that's negative 6. Okay, questions with that so far? Okay, so now we apply f inverse of a. We want to find the derivative of that is the reciprocal of 1 over the derivative for our original function times b. So that would be the same thing as if, so I'm going to rewrite that. F, our inverse, in this case, a is 7, right? A is 7. 7, and all that is the derivative to that equals to 1 over the derivative to 6 to the negative 1. Okay, so that's this. Okay, and so basically we found that the derivative of negative 1 is going to be 1 over, so we found this to be negative 6, so it's 1 over negative 6, and that's our answer. Okay, so that's a whole lot simpler than what we did yesterday. All right, questions with that? Okay, so all righty. So let's look at another problem. Let's look at problem number 67, where we have sine x. Okay, and so we're operating between negative pi over 2 and pi over 2, where a is 1/2. All right, so let's look at that. So number 67, we have f of x equals to sine x, where we're looking at from negative pi over 2 less than or equal to x, and that's less than or equal to pi over 2. So if you look at the unit circle, right, here's negative pi over 2, and here's positive pi over 2. So we're operating between either the first or the fourth quadrants, okay? And we're given a equals to 1/2. Okay, questions with that, excuse me, so far? Okay, so basically this is, we just replace f of x with y, right, equal to sine x. Well, y is the same thing as a, right? So we're going to put in here, so we have 1/2 coming out, but we don't know what our x value is. So we got to solve for that. So we replace the a with 1/2 equals to sine x, right? And so we apply the inverse sine to both sides so that the sine and inverse sine cancel each other out, and we just get x equals to, so this is a this is inverse sine of 1/2. So that means we're given the value and we're trying to find the angle. Well, if you look at square root 3 over 2 and 1/2 for cosine and sine, that's at pi over 6. So sine, inverse sine is 1/2 at the angle pi over 6. Okay, so here when we're on this side, we have the value and we're looking for the angle. When we're working with inverse sine, we're given the value and we're looking for the angle. So that means our angle is pi over 6. So this is our B and A. Okay, so we're saying here that f of pi over 6 equals to 1/2, and the inverse 1/2 equals to pi over 6. Okay, so from here we need to find our derivative. Okay, so I'm going to rewrite this. F of x equals to sine x, and so the derivative for sine is just cosine x. Okay, so if we were to apply, so from here we go ahead and find what that derivative is, for x, we said is pi over 6. So that would be cosine at pi over 6. And cosine at pi over 6, right, is square root 3 over 2. So that's square root 3 over 2. Okay, questions with that so far? Okay, so we're said that the inverse, the derivative of the inverse, right, our inverse is 1/2 is equal to 1 over, and that's the derivative for that, is equal to the derivative, the reciprocal of f prime at pi over 6. And so that's going to make it, so we said that that is square root, is 1 over square root 3 over 2. So that would be the same thing as if we said cosine of pi over 6 equals to 1 over square root 3 over 2. So because we have to apply the reciprocal, right, we're going to flip that. And so that becomes 2 over the square root of 3. Okay, any questions with that? Because it's like 1 divided by the square root of 3 over 2, right? So we have to multiply the reciprocal. Well, we need to rationalize that. So we have to multiply the square root of 3 over the square root of 3 because the radical in the denominator is not simplified completely. And so we get 2 square root 3 over the square root of 9, right? Which the square root of 9 is 3. So our answer is 2 square root 3 over 3. And that's our answer. Okay. Any questions with that? Okay, so that is lesson 5.3. And we're going on to our last lesson of the course, 5.4. And so let's take a look at that. So I put PowerPoint slides on Blackboard. Did anybody get to see those at all?
No.
No?
I haven't checked lately.
So take a look on Blackboard. I have all the PowerPoint slides since the beginning of the course on Blackboard now. Okay. So you want to go ahead and take a look at that. All righty. So let's see, how are we doing for time? All right. We got a couple of minutes before we have to switch. Okay, develop the properties of, okay, so we're looking at 5.4, exponential functions, differentiation, and integration. Develop properties of the natural exponential function, differentiate natural exponential functions, and integrate natural exponential functions. Okay, so the definition of a natural exponential function is the inverse function of a natural log. Well, natural log is really nothing more than, natural log is nothing more than log x base e. Well, e is basically 2.71 as a decimal, rounded off to 2 decimal places. All right, so why is e significant? Because e, if you compound it, e gets into compounding continuously. If you compound something continuously, basically every 15 seconds, then you get 2.71. And so that's why E is significant. So we look at that in nature when we're looking at something on a continual basis, it tends to go to E. So natural log is called the natural exponential function and is denoted by, so the inverse of natural log is E. So if we took natural log x base E, and if we took log E to the x power base E, these two cancel each other out, we get x. So if we took E to the natural log x power, again, these are inverses, we get x. So E and natural log are inverses of each other, okay? So y equals e to the x, y is equal e to the x, if and only if x equals the natural log y. And that's because the y is e, and the e's cancel each other out, and you just get x, okay? Working with properties of logarithms. All right, the inverse relationship between the natural logarithmic function and the natural exponential function can be summarized. Natural log e, and that's what I was saying here. Natural log e to the x is nothing more than e to the x base e. The e's cancel because they're inverses, and you just get x. Okay, and e to the natural log x is x, and that's what I did here. Okay. All right, any questions with that? So this establishes that log and natural log are inverses of each other. Okay, so we want to solve for x accurate to 3 decimal places. Let's take a look at problem 10. Okay, so let's do that. Where did I put my, here it is. Okay, so put this up on number 10. Okay, we've got 100 e to the negative 2x power equals 235. Okay, so let's exit and come back, and we'll continue with this. All right.
Mr. Janzak,
Yes.
this Kiara, I have to be to work at 9, so I won't meet on the second Zoom. I'm about to get ready to leave my room.
All right, Kiara, let me make sure I got you on my sheet.
Okay.
Kiara.
Humbert.
Yeah, I have you.
Okay, thank you.
All right, you're welcome. Okay, so let's exit and come back.